Imagine waking up to a universe where half of everything you know, planets, people, the ground beneath your feet, even the cup of coffee in your hand, has simply vanished. It is not science fiction, but for decades, this scenario was a haunting reality for cosmologists. The universe seemed to be playing a cosmic game of hide and seek with its most fundamental building blocks. Where was all the missing matter? And what would its absence mean for our understanding of the cosmos, and even for the very laws of physics themselves? To grasp the scale of this enigma, let us rewind to the basics. Everything you experience, earth, water, air, and stardust, is what physicists call ordinary matter, or baryonic matter. It is the matter made up of protons, neutrons, and electrons. But here is the twist. Scientists have learned that all the glowing stars, swirling planets, swirling clouds of gas, and even you, make up only about 1/6 of all matter that exists. The rest, an astonishing 5/6, is an entirely invisible ingredient known as dark matter. Dark matter does not emit, absorb, or reflect light, making it undetectable by conventional telescopes. We know it is out there only because of the way its gravity tugs on the stuff we can see. But the mystery runs even deeper. Even within that small slice of ordinary matter, experts realized decades ago that the universe was hiding something. Predictions made by the Big Bang Theory and detailed measurements of the cosmic microwave background, the afterglow of creation itself, told astronomers exactly how much baryonic matter should be out there. Yet every careful census of stars, gas, and galaxies fell short by at least half. In other words, if you counted up all the ordinary matter in the universe, you would find only a fraction of what theory says should exist. It was as if the universe had whisked away its own furniture, leaving only echoes behind. This missing matter problem was not a trivial gap in the textbooks. It was a puzzle that threatened to undermine our entire understanding of cosmic history. If we could not account for so much of the universe's basic ingredients, how reliable were our theories about galaxy formation, cosmic evolution, or even the ultimate fate of everything? Over the years, the search for the missing matter took on the urgency of a cosmic detective story. Astronomers scoured the night sky using ever more powerful telescopes, peering deep into the hearts of galaxies and far out into the voids between them. They cataloged billions of stars, mapped the intricate structures of galaxy clusters, and measured the glowing filaments of gas that thread the cosmos. But no matter how hard they looked, the numbers stubbornly refused to add up. Some researchers suspected the missing matter might be hiding in the vast, almost ethereal web that stretches between galaxies. This structure, known as the warm-hot intergalactic medium, WHIM for short, is a plasma of gas heated to millions of degrees, so sparse that its atoms are spread across volumes larger than entire galaxies. This cosmic fog is so tenuous that it barely interacts with light, making it nearly impossible to detect with traditional telescopes. X-ray satellites sometimes caught fleeting glimpses of it, but their measurements were plagued by interference from closer sources. Computer simulations, like the groundbreaking Illustrious TNG project, predicted that as much as 3/4 of all baryonic matter should be hiding in this intergalactic web. Yet, until recently, the evidence remained frustratingly out of reach. The missing matter debate became so heated that some scientists began to question whether our understanding of physics might be incomplete. Was there something fundamentally wrong with our models of how matter evolves after the Big Bang? Could the laws of nature themselves require a rewrite? Others speculated about entirely new forms of matter or exotic physical processes. The stakes were nothing less than our grasp of reality. But whatever their source, FRBs have a unique superpower. As their radio waves race across the universe, they pass through clouds of gas, plasma, and dust. Each atom along the way slows down and stretches the signal just a tiny bit, a process known as dispersion. By the time the FRB reaches Earth, its signal has been smeared out in a way that encodes a perfect record of every obstacle it encountered. Liam Connor, an assistant professor at Harvard and co-lead of a landmark study, put it this way: fast radio bursts shine through the fog of the intergalactic medium, allowing us to weigh it. In other words, these cosmic flashlights turn the invisible into the measurable, letting us map the otherwise hidden matter between galaxies. Vikram Ravi, an astronomer at Caltech and another pioneer in the field, offered an evocative metaphor. FRBs act as backlights, illuminating the shadow of all the baryons. Imagine standing in a dark room with only a faint outline of a figure cast on the wall by a distant light. You cannot see the person, but you know they are there, and you can begin to deduce their shape and size. FRBs do the same for the unseen atoms in the universe's vast spaces. To put this method to the ultimate test, a collaboration between Caltech and the Center for Astrophysics at Harvard and the Smithsonian marshaled an array of innovative instruments. Their principal tool, the Deep Synoptic Array, a network of 110 radio telescopes nestled in California's Owens Valley. This technological marvel was designed specifically to hunt for and localize FRBs, pinpointing their origins with unprecedented precision. Out of more than 1,000 fast radio bursts detected by astronomers worldwide, only a select group, fewer than 100, have been traced back to their exact home galaxies. This is a crucial step, because only when you know both the origin and the precise distance of an FRB can you measure the amount of matter its light has crossed. In their landmark study, the team successfully mapped the journeys of 69 FRBs, some of which traveled nearly 9 billion light-years before reaching Earth. To put that in perspective, these signals began their journey when the universe was less than half its current age, long before our sun and solar system had even formed. The process is both elegant and mind-boggling. Scientists meticulously analyze how each FRB's radio signal spread out as it traversed the cosmos. The more matter it passed through, the more dispersed its signal becomes. By comparing FRBs from different distances and directions, astronomers can reconstruct a three-dimensional map of the hidden gas and plasma that fills intergalactic space. What the researchers discovered was both astonishing and deeply satisfying. Their analysis revealed that about 3/4, specifically 76%, of the universe's ordinary matter is not locked up in stars, planets, or galaxies, but instead drifts in the intergalactic medium. Another 15% resides in diffuse halos that surround galaxies like invisible cocoons. Only a tiny remainder, less than 1/10, is packed into the luminous stars and cold gas that make up the visible parts of galaxies. These findings finally bring observations into alignment with decades of cosmological simulations. The missing matter has been found, not as a hidden stash within galaxies, but as an ocean of tenuous gas threading the cosmic web. It is as if we have finally switched on the lights in a vast, dark warehouse and discovered the crates and boxes we always suspected were there. But what does this breakthrough really mean for our understanding of the cosmos? First, it validates our most fundamental models of cosmic evolution. The predictions from the Big Bang, the intricate calculations underlying the cosmic microwave background, and the results of advanced computer simulations now all converge. Our picture of the universe's composition is more complete and accurate than ever before. Second, the ability to map the distribution of ordinary matter has transformative implications for the study of galaxy formation. Galaxies do not exist in isolation. They are constantly fed by streams of gas from the intergalactic medium. Understanding how this hidden matter flows, condenses, and ignites new generations of stars is crucial for unraveling the life cycles of galaxies. As Bruce Drain, a theoretical astrophysicist at Princeton, puts it, understanding the distribution of baryons is crucial for galaxy formation models. Third, and perhaps most excitingly, the techniques pioneered with FRBs open up entirely new avenues for exploring some of the deepest mysteries in physics. For example, precise measurements of how ordinary matter clusters and disperses can help pin down the mass of neutrinos, ghostly subatomic particles that barely interact with anything, yet flood the universe in unimaginable numbers. The standard model of particle physics once assumed neutrinos were massless, but experiments have shown they do have a tiny mass. Knowing exactly how much could reveal new physics beyond what we currently know. Renan Barkana, a cosmologist at Tel Aviv University, believes that FRBs may even allow us to study the universe's earliest epochs, such as the era of rayonization, when the first stars and galaxies lit up the cosmos and transformed the intergalactic medium from neutral hydrogen to a sea of charged particles. By analyzing FRBs from progressively greater distances, astronomers may one day reconstruct the timeline of how the universe became transparent to light, a story written in the faint whispers of ancient radio waves. The implications ripple outward. Wendy Friedman, a pioneering cosmologist at the University of Chicago, emphasizes that even our measurements of the Hubble constant, the rate at which the universe is expanding, depend on knowing exactly where all the matter is. The more FRBs we detect and localize, the sharper and more reliable those measurements become. Accurate models of the universe's expansion are not just academic. They shape our predictions about the fate of everything, from the ultimate destiny of galaxies to the possible end of time itself. Looking ahead, the future for this line of research is dazzlingly bright. The Deep Synoptic Array is only the beginning. Next-generation telescopes, such as the planned DSA 2000 in Nevada, will be able to detect and localize up to 10,000 fast radio bursts every single year. That is more than 100 times the number detected so far, opening the door to a true three-dimensional map of the universe's hidden scaffolding. With thousands of new FRBs illuminating every nook and cranny of the cosmic web, astronomers will be able to study not just where matter is now, but how it moves, evolves, and interacts over cosmic time. This could reveal how galaxies grow by accreting gas, how black holes shape their environments, and even how the large-scale structure of the universe emerged from the quantum fluctuations of the Big Bang. The benefits are not limited to pure science. The techniques developed for tracking FRBs, advanced data analysis, real-time signal processing, and machine learning algorithms are already inspiring innovations in fields as diverse as telecommunications, medical imaging, and artificial intelligence. The challenge of sifting through the vast torrents of data generated by radio telescopes has led to breakthroughs in big data management and pattern recognition, technologies that ripple into our everyday lives. There is also a powerful human dimension. The story of the missing matter is, at its heart, a tale of curiosity, perseverance, and ingenuity. It shows how the deepest mysteries often require not just new instruments, but entirely new ways of thinking. What was invisible yesterday can become the foundation for tomorrow's discoveries. The very act of searching for the universe's hidden matter has pushed the boundaries of technology and human imagination alike. And the quest is far from over. As we refine our maps of the intergalactic medium, tantalizing questions emerge. What else might be lurking in those vast, nearly empty spaces? Could they harbor clues about the universe's earliest stars, so-called population 3 stars, forged from pristine hydrogen and helium in the cosmic dawn? Might we detect signs of exotic physics, like changes in the fundamental constants of nature, or even evidence of interactions between ordinary matter and the mysterious dark matter? As Christopher Martin of Caltech observes, instruments like the Keck Cosmic Web Imager are now probing the filaments of gas streaming into galaxies, offering a complementary view of the cosmic web. By combining optical and radio observations, astronomers are piecing together a more complete picture of how matter cycles through the universe, from the smallest scales of star formation to the grandest structures spanning hundreds of millions of light years. There is also the tantalizing prospect that fast radio bursts could serve as cosmic probes for yet undiscovered phenomena. Could they reveal the fingerprints of ancient explosions, the echoes of primordial black holes, or even the subtle imprints of quantum gravity? As we build ever more sensitive telescopes and refine our analysis with the power of quantum computing and artificial intelligence, the possibilities expand. For educators and students, these discoveries offer a living example of how science advances, not in straight lines but through detours, dead ends, and sudden leaps of insight. The missing matter mystery that baffled generations is now becoming a cornerstone for new explorations. As more data pours in, textbooks will need to be rewritten, and new generations of scientists will face the challenge of interpreting a universe that is at once more familiar and more mysterious than ever before. For the public, the story is equally inspiring. It is a reminder that the universe is not just out there, remote and unchanging, but something we can probe, map, and ultimately understand. The same technologies that let us track fleeting radio bursts from billions of light years away are fueling innovations that touch our daily lives, from better medical diagnostics to smarter navigation systems. So, what comes next? The discovery of the universe's missing ordinary matter is not the end of the story, but a thrilling new beginning. Fast radio bursts, once considered cosmic oddities or even nuisances, have become our brightest beacons, guiding us deeper into the unknown. The more we learn, the more we realize how many secrets remain, waiting to be uncovered with each new observation. The next time you gaze up at the night sky, remember, the twinkling stars are only the tip of the cosmic iceberg. Most of the universe's ordinary matter is not in those shining points, but in the vast, invisible spaces between them, now illuminated by the fleeting signals of fast radio bursts. Thanks to the ingenuity of astronomers and the power of modern technology, we are finally beginning to see the universe as it truly is, interconnected, dynamic, and full of surprises. And here is a secret that few outside the scientific community know. The same techniques used to track down missing ordinary matter could, one day, help us detect the elusive dark matter, or even glimpse the aftershocks of ancient cosmic events that shaped the universe's earliest moments. The dream of mapping the cosmos in exquisite detail, a vision once confined to science fiction, is becoming reality, one fast radio burst at a time. What do you think the next great cosmic mystery will be? Could it be the true nature of dark energy, the fate of the universe, or something we have not even imagined yet? Share your theories and questions in the comments below. And if you enjoyed this journey through the frontiers of astronomy, do not forget to subscribe and join us for more mind-expanding discoveries.